Right, I thought what I'd do today, rather than going through a presentation, is kind of walk through what you might do if you want to get an application that you've written, maybe something written, a piece of analysis software that you've done in R or Fortran on your laptop, running on an HPC system, or maybe your supervisor has been to a conference and said, I saw this presentation, there's this piece of code we should be looking at, we should be trying to see if we can use this in our study. Here's a GitHub repo, get on it. And for the purposes of this, I'm going to use a little program I wrote a while back. You'll see that some of the earliest commits are from 6 years ago, but certainly the latest are as far as about a year ago. And what this is an implementation of a cellular automata program called Conway's Game of Life. It's intended to run on this tiny little laptop, which I've got, which is a thing called an EPC. It's actually the first netbook that was ever produced. And I run an operating system on it called FreeDOS, which is an open source version of the Microsoft DOS operating system. It has a Fortran compiler, which is good, but the Fortran compiler is Fortran 77. So when I wrote this program, I wrote it in Fortran 77, even though it was, the current era. And I made use some of the nice features in DOS that let you use the character set to display sort of pseudo graphics on the terminal. The other nice thing I did was I did make sure it actually compiles on Linux, so we don't have to do any difficult porting. And on Linux, it again similarly makes use of sort of block characters and so forth to draw graphics. I also did a version which makes use of the UTF-8 Braille character set, because that is quite cool, and it lets you have like a denser image inside your terminal. So, what is Conway's Game of Life? So Conway's Game of Life is a really cool and fairly old cellular automata program. And what that means is it creates a field of cells, which are squares, and it has a set of rules that every time step look at the surrounding cells and decide whether that particular cell is alive or dead. And it's been around for a long time. It gives rise to some really interesting behaviors and some kind of like really cool patterns. So obviously there are structures which don't do anything, right? They just remain in a steady state. You get these structures which oscillate, which are quite cool. And perhaps even more interesting, you can create structures called spaceships, of which the most famous is the glider, which travel across the cellular grid as times. They have a repeating pattern that also moves in a direction, usually diagonally. There are even more complicated constructs. So this is a thing called a glider gun. And what the glider gun does is it creates gliders about here, and then they travel across the screen. There's also a construct called the eater, which consumes gliders. And so you get all these cool, interesting features, right? So this is what the application does. So let's have a look at the application, right? So I've got my laptop here. I've got a terminal. I actually have the code on my laptop because of course I developed it. If we have a look at the files in the directory, there are some exe files. That's because I built it a while ago. Let's clear those out. Okay, so the code as you get it has a bunch of Fortran code. It's both Fortran 90 and Fortran 77. There's some make files. There's this make file in capitals, which is for Whatcom. So that's how you build it on DOS. If we actually look at how do we build it in Linux, well, if we look at the instructions on the README back here in GitHub, we see that on Linux you run make -f makefile.gnu. So let's do that. And it compiles, right? There's a Fortran compiler on this machine, so that's fine. The exe files we end up with, there are two programs here, Life and Show. Life is the main simulation. Show lets you see some of the image outputs. There's both the normal .exe versions, which they're .exes because normally I run this on DOS, right? So it creates the same executables. The Braille so the .exe ones use the normal terminal blocks to generate graphics. The Braille ones use Unicode. There's also some tools here starting with Gen. There's a program for creating a blank image and a program for creating a random image. And so why am I saying images? Well, the way this is designed, if we look in the input folder, they take in an image format called PBM. And PBM is quite cool because it's kind of a really stupid image, but most very basic image format. So if we look at the glider, for example, it's plain text, which is very space inefficient, but you get a header file which basically says the type of image, usually P1, P2, or P3. P1 is black and white, like this. P2 is grayscale. I think P3 is color. You can then have comments in the header, and then you have the dimensions, and then you literally have the pixels written out as ones and zeros. And in this case, you can see the little glider shape here in ones. So we've got the code built up. Let's run it, right? So if we run life.exe and we run it on the eater, we get it drawn on the screen, we get this is like the initial state, and every time we press return, we step to the next iteration, right? If we hold down return, you'll see that you generate these little gliders. So you have the glider gun up here, it generates gliders, it fires them into the eater, and the eater consumes them. Right. You'll see that there's some generation and population information. This is quite nice later on when we want to do our study, in quotes. Because what we'll try and do is run a bunch of these and then get some data about the populations. Okay. Show obviously just shows the images. So, for example, if we do this, the Braille versions do it in Braille. Right, so that produces a smaller image, so you can get more in the terminal. Gen blank generates a blank input image, so that just makes it easier to edit. And genrand is going to be important because what that does is use the random number generator to generate some random images. So how does that work? So if we run genrand, the nice thing about my shell is it kind of autofills into things you've done before. So genrand takes a bunch of arguments. These are the dimensions of the image you want to create, the probability that a cell is alive, and then the random seed, and then the file name. So the random seed is quite important because when you generate random numbers on a computer, they're not really random. What they are is you have a starting number called the seed, and then an algorithm which generates randomly distributed numbers from that point. You might go, well, I use some programming language like, I don't know, Python or something where I call random and I get a random number, right? That's not really random, it's done in the same way, but the seed is some predefined sort of randomy thing. So it might be the date or the time or some combination of the time and the machine name. It depends very much on the implementation what this is, right? But here we're directly controlling the seed. So it's saying the seed is 1, 2, 3, 4, which means that when we run this program, it will write an image, and then if we show it, oops. Right, it's a particular random distribution. If we generate something with the same seed, we should get exactly the same image, right? So let's do that. Yeah, it's the same image. So what happens if we change the seed? So let's add 1 to the seed, just to prove we get a different image. And then if we show that, oops, what did I do wrong there? I showed the wrong image. Let's show 2. We see it's a different image, right? What else do we need to know before we can run a job? So, life takes a bunch of options itself. It doesn't just take the file, it can also take the two important things for this. It can take as well as the input file, we can give it a number of iterations to run for, let's say 10, and then we can give it a mask, which means it will write out images. So let's just call them the mask junk out. And then when we run that, instead of running the simulation graphically, what it does is it writes out more PBMs, right, with the generation, with that mask as the starting name. So now if we show those, for example, that's number 10, right? And what that kind of shows you is when I wrote this, I was already thinking about this, right? How do you write a batch job and get the output from that in a sensible way? So that's good. So we've played about with this on our computer. Let's bring it onto Myriad and then do some actual, try and submit as a job with an array and get some output from it. So first, we have to grab the code. So let's do that. Here we are on GitHub. On GitHub, you go to code here, and then it'll give you an HTTPS URL. If you copy that, you clone it with Git. If you look, we still have a folder called FortLife. Our files are all there. So how are we going to compile it? So Myriad has a bunch of different Fortran compilers. Most of them are quite efficient, but the problem is, so for example, the Intel compiler is much more efficient than the GNU compiler, so is the NVIDIA compiler. The problem is they don't handle the Unicode output very well. So let's build it with the GNU compiler. By default, there's a very old version of the GNU compiler in the path. It is version 492, I think. Yes, which is 7 or 8 years old now, but it's new enough to compile this. So let's, for ease of use, let's compile it with this. Let's do make -f makefile.gnu, and just as it did on my laptop, it compiles the code, right? The next thing we want to do is think about how we're going to construct our job, right? So let's say we want to run 100 input values of a random set of completely random images. How do we do that? So the first thing we need to do is write a job script, right? So if we we'll call this something like life study .sh, and then we'll do, so every shell script needs a shebang, and that's true for job scripts as well. We need to make sure it's a login shell because it's a job script. We need to give it a runtime. Let's assume it's going to take less than half an hour. It's probably going to take less than a minute to generate this reality, but let's just give it a nice upper bound. So $$ -l hrt equals, oops, it's h_rt 003000. We need to give it an amount of memory. Again, this is a thing that runs on my little netbook. My netbook has, I think, 256 or 512 megabytes of RAM. It's a long time since I've cared, because that, of course, on DOS is basically infinity. Let's just give this 2 gigabytes to be safe. We should set an tempfs value. Let's say, again, something very small. Let's just say 1G. We're not actually going to use that, but it's good to set that because some temporary files will get written there by the job. Let's run it in the current working directory, and let's give it a name. So if you do $-n, you can give it a nicer name than the name of the shell script. So what are the steps we want to do? We want to generate a random image, and then we want to run life on it. So we want to do /gen_rand.exe. And then we want to give it let's give it the dimensions, let's just be nice to not use too much CPU time and do like 50-50, right? We need to give it the probability that cell is alive. My experience is around about 0.2 gives some quite nice patterns. Let's give it 0.25. And then we need to give it a seed. And if you think back to what I said we want to create an array of jobs. And the way we do that is using a construct in Grid Engine called job arrays. Let me dig that out. So how do you use job arrays? Well, let's go to the UCL Research Computing documentation and go to example job scripts. And if we scroll down, there's an example here called array job. And that tells us 2 important things. So an array job is a setup where you run one shell script, and that the scheduler creates lots and lots of copies of it, and those copies have a task ID, which you set in the shell script, and that becomes an environment variable inside that copy of the job. So, to cut a long story short, what that allows us to do is we say, back up here in our things, we want to, let's say we want to run, I don't know, seeds between 501 and 600, right? Let's do something that's fairly non-standard. So that should create 100 jobs, and then we want to use that environment variable we just saw, SGE underscore task ID, to set the seed. Right. One like stylistic thing in shell scripting, it's slightly more explicit if you put the curly braces around the variable. You don't have to do that in this example because there are spaces, but if you're doing things where you have the variable inside the name, like you will later on in the command, you might have to do that. And then finally we need to give it a name, and so we'll create a folder called output, and we'll call it input dash then dollar. Let's do that. Oops. Slight Vim moment there. Right. So that should create an input file. So for each copy of this job, we'll create an input file whose seed is the task ID. So job if the task is task 508, the seed will be 508. The output file will be input dollar. Oops, there's a typo there. SG underscore task ID.pbm, right? So we should end up with 100 input files, and then we want to run the life executable on that as well. So if we run life.exe, the input file, which is this file that we've created here, we want to, let's say we're going to run it for 1,000 time steps, and we want to put the actual images in output, oops, slash step task dash step. And that should produce images which have a labeled with the task, with the seed effectively, and the step, right? And that's our job script, right? We should make that output folder. And then let's try submitting our job and see if it works. Qsub, I'll call it lifestudy.sh. That's our job submitted. It's in the queue. So when this is run, I will come back and record the second half of this video. Okay, so a little bit later and we're back, and let's have a look, see if our jobs are run. In slightly different rooms, the screen's on the wrong side, but that's okay. If we do qstat, we can see that we now have an empty list. That means the jobs have run. And if we do an ls, we'll see there's a huge chunk of output files, right? So if you see my other videos, you know that the .e files contain the output of standard error, and the .o files contain the output for standard out. We have one for each task that you ran. So you ran 100 tasks, there's 100 standard output and 100 standard error files. Let's just pick an output file at random and see if that worked. So we cat that, it looks like it ran. Okay, so let's see, did we get output files in the output directory? Well, that's going to be a long ls. There's actually quite a lot of files in there, because if you think about it, there is 100 jobs times 1,000 files. So I've probably just hung that output. It's a lot of data. It's about 800 megabytes. A lot in quotes. But anyway, right. So the next part of this is kind of, we want to take a look at this stuff that we've done and see if we can do some kind of analysis on it, right? And what I thought we would do is, if you look at the output, you'll see that we print out each generation the population. And you see this one has kind of stabilized at 82. And my experience of this is generally they do kind of stabilize. So what we'll do is we want to get that data out of the output file, convert it into a CSV, and then just to show off, I'll bring it to a Windows machine and we'll try and do some graphing in Excel. Okay? So, we have all these output files. So we do as star o star. You see all the output files. And what we want to do is we want to get just the bit that says population out of those files. So how do we do that? There's a lovely Unix command called grep, which searches for things. So if we look at one of these files, what we want to do is grep out populate the line that contains the word population, right? So if we put that through grep, oops. So when we do that, right, we have it print out just the lines that contain the word population. So what we want to then do is turn this into a CSV file, right? And a CSV file is a file of values separated by commas, hence comma separated, right? And to do that, we want to pull the numbers out of this data and use that to produce a file. So let's think about how we can do that. So we get those lines with grep, right? And there's another program called awk, which lets you muck about with streams of text. So let's do that. So let's do a very simple awk command. If we do awk and then print out the columns we want, so awk numbers the columns from left to right, right? And it assumes there's space separated. So if we look at this, the time step number is the third value, so you want to do $3, and then to force it to print out a comma, we'll put a comma in quotes there, and then the population value is in column 5, so you want it to print out column 5. Let's see if this does the right thing. There we go, okay? And then if we redirect that to a file, we then get a CSV file. So we want to automate that a bit, so we want to have it in a loop, okay? So how are we going to do that? We have files with names from 501 to 600. There's a Unix command called seek, which will generate a set of numbers like that, right? And we want to do a loop. So let's do that. So for a in, seek 501 to 600, do. Now we want to do that entire command and output the value to a text file. Okay, so we have cat life study.o, the value, $. Remember, we've done this before, $A. Okay, that should give us the output file through grep population through awk print $3 $5 and then into a file, right? We've got pop $A.csv. Just think in our heads, did we do the right thing there? We've got the full name of the file, should be correct. Getting the right line, that is the correct construct to print, and let's put it into the file. Right, if this works, it will be very surprising. Okay. We have a bunch of CSV files, let's cat one of them. If we cat the corresponding life file, we should believe that it is the same data. Yeah, it levels off at 69. Good, so we have those files. So we've got the CSV files, but if we want to graph them, we really want one file. So how are we going to do that? There are a bunch of Unix tools you can use to mangle files together. But let's be a bit creative because I'm bored. Let's do this in Python. So let's bring Python into our environment. And I'll bring in Python 3.9. Okay, now when we run IPython, we should get a Python 3.9. Oops. There we go. Right. Python has some nice modules for loading CSVs, and you can get them by doing import CSV. Okay, that's our environment. We probably want to store our results in something, so let's create a dict. You can see it's auto-filling because I was testing this earlier, so I'm not doing this entirely in the live sense. Then we need to read in the file, put all the files, put them into data in the CSV that we want, and then restructure that in memory and write out as a new CSV, right? So if we do, let's think about what that looks like. So presumably we want to have a loop for a in range, and the Python range starts at 0 and goes to the upper level, and there are 100 of them, so we want to do range 100. Oops. Right. Then we need to generate a file, an ID, so we'll call that, so if it starts at 0 to 99, but our files are numbered 501 to 600, we want to do ID equals a plus 501. And I've messed that up, and that's because I've forgotten the A. Right, let's do that. One of the really nice things about using IPython as a thing here is it lets you edit stuff, right? Then we need to create a file name for that. So fn equals, what do we call it? Pop. Pop plus string form of A, of ID, sorry, plus the .csv. You notice that because I use other programming languages a lot, I have this bad habit of using double quotes around strings in Python. It works, it's not really a problem, that's just that I imagine there are Python people who look at that and want to punch me in the face. I'm sorry, okay? I use actual programming languages a lot of the time. We then need to do this clever construct that Python has, which kind of safely keeps a file open until only as long as you need it. So if we open the file, we've got, whoops. And then we read that in. We want to make sure the results are blank. So in the results, well, the way we're going to structure this is we're going to have a dict essentially of dicts. The outer dict is the complete record set, and each dict is like a trajectory from a simulation, right? So we want to create a blank dict for this record set, and then for every row in that file, we need to read that in and put that into that record set, okay? Now there's a thing you have to do here, which is that some of the rows are empty because of the processing, so we need to make sure we don't try to process empty rows, because we're going to use explicit row IDs because we're bad programmers, and that will cause it to crash. So we say if len row equals greater than 0, so only proceed if there's actually data in the row. They will then add that into the results file, right? And we double check that several times to make sure that looks okay, and then we press return and return again. So did that work? Let's see what results look like. Ooh, that makes me very unhappy. Ooh, there we go. It's quite a big file. So that's all our data. Right. Now we want to write that out to a CSV. So what we want to do is loop over the keys in the dict, and then loop over the keys inside that, and write that as a file. So our next line is with open out.csv, wcsv file. TW. So for every trajectory in there, right, we want to create a blank list. We want to add the key. So the first entry in the row is the actual trajectory name. So we do temp list.append a. And then we need to go through the trajectory, adding it to the list, right? For then, slight annoying anti-feature by Python, we need to go back, TW, and then we write the row out to the file. So the question is, did that work? Another nice thing about IPython is you can run shell commands in it, so let's see if that worked. We indeed have an incredibly massive CSV file. Right. Now, what we're going to do, I think I will boot up Windows, and then we'll bring this file back to Windows and play with it in Excel. Okay, so I've booted up Windows, I've opened a terminal window, and I've used SFTP to connect to Myriad. If we go into the directory we were in before, it's in Scratch. Oops. One of the SFTP is very primitive. It doesn't have autocomplete, which is very annoying. I believe the folder is no, I don't know. Actually, let's have a look. Right, it is in live-webinar. There we go. And now if we get the file, that should bring it back, and we should have this data file on our desktop. Now, the nice thing about CSV files is that Excel can open them. It'd be quite interesting getting Excel to open a file this big. Let's see what happens. There's our data, nicely split down. We have the trajectory number down the left, and we have the actual population information down the right. So if we graph that, let's actually just delete this row because I fear creating problems in the chart. If we graph the chart, there we go. Excel, of course, defaults to making horrendous looking charts. Let's tidy this up a bit. We probably want to get rid of the legend. You can see this is the tracked population, right, for each of our runs. You can see that some of these enter a stable state fairly on, some of them wobble about, and I'm sure if we were doing this on real data that we cared about, we'd come up with some much more interesting observations. Anyway, so there you go, right? There's how you take a piece of code, run it on the cluster, do some quick analysis of your results, and hopefully publish a paper and bring in lots of research funding.